This is midterm 2B from spring 2025, a reflection and transmission problem. The question states, a left-hand circle polarization of 15.92 gigahertz is incident from the air onto a block of material, Z is less than 0, with a complex permittivity of 36 minus J 4000 epsilon naught, at an incident angle of 60 degrees. The amplitude of the initial H field is H naught is equal to 5 milliamps over meters. Write the full expression of A, the incident E field, B, reflected E field, and C, the transmitted H field. And so, given with this problem, we will be given the diagram shown as medium 1 and medium 2 in the Y and Z plane. So the first thing to solve for in this reflection and transmission problem is to find the loss tangent. And so the loss tangent will help us determine if this material is low loss, lossless, or a good conductor. And so using the equation, loss tangent is equal to epsilon double prime over epsilon prime. And so we were given the complex permittivity. And the complex permittivity tells us that 36 is epsilon prime and J4000 is epsilon double prime. And so we know that epsilon prime is also known as the dielectric constant as well. And so plugging these two into the numerator and denominator, the loss tangent becomes 111, which is greater than 100. And so therefore this is a good conductor. And to note that good conductors cannot use any formula that has the index of refraction, which is just the letter N, which I'll explain more once we go into this example. And so after finding the loss tangent, we can now know what to look for. Since we have a good conductor, we need to find the following parameters, which is the attenuation, or alpha. And so once we solve for alpha, right, we can be able to use that to find for eta. But first, we need to find the conductance. So we used the loss tangent is equal to the conductance over omega times epsilon. And since we solve for loss tangent, which is 111, we equal that to this equation. And in order to find omega, we need to use the frequency given to us. And so this is 15.92 gigahertz. And so we can use the following equation, omega is equal to 2 pi times frequency, in order to convert frequency into omega, or as I learned from, you can just count how many values are before the decimal. So we have 1, 2, and then count how many values the gigahertz has. So we know that megahertz is 6, and so gigahertz is 9. And so therefore we add these three. 1 plus 1 plus 9 is equal to 11, or omega is 10 to the 11. You can as well solve for omega as 2 pi times the frequency. And so once we're done with that, we can find the conductance. We separate the terms, omega and epsilon, over to the left-hand side. We plug them in. Epsilon becomes epsilon naught times epsilon r, which is also the dielectric constant. Epsilon naught is a given constant known as 8.84 times 10 to the negative 12. Epsilon prime is known as 36, given by the complex permittivity in the in the problem. And so the conductance becomes 3,532. Once we find the conductance, we are able to solve for alpha. And so solving for alpha, the equation is known as this. Alpha is equal to beta, which is equal to the permittivity times omega times the conductance, all over 2, square root. We know that permittivity naught is 4 pi times 10 to the negative 7. This is also a given constant. We already solved for omega, and we already solved for the conductance. And so plugging this in, we get a value of 149,000. And so after solving for this, we can find eta, or the complex eta. And so eta, or known as the ratio, is known as 1 plus j times alpha over conductance. And so 1 plus j becomes square root 2, and alpha over conductance is just 149,000 divided by 3,532. And since we're dealing with complex number, we will get a phase shift of 45 degrees. And the reason why I label this as eta 2 is because this eta 2 is the ratio in this medium, right? Because again, we're dealing with good conductor. And so based on this, we can solve for part A. So for part A, we need to find the incident E field. And by doing this, I already drew the graph and the axis and which direction the E field goes to. But to simplify this, the main graph we're dealing in is the Y and Z axis. We know that the X axis is into the page. Based on this, we know that the X cross Y is equal to Z hat, right? Or we can think about it as Y cross Z is equal to the X hat. And so knowing this format, we know that positive X is going into the page. We know that our wave vector, our wave vector is going at a diagonal into the medium. And since this is the medium right here, as I drew poorly, this angle, or incident angle, is 60 degrees. And we know that this is parallel with this, therefore this becomes 60 degrees as well. And we were given that the H field, or H naught, is also into the page. And so therefore, based on H is going into the page and the wave vector is going at an angle, we can determine where the incident E field goes to. So based on your right hand rule, the K is our thumb, the H field, right? H incident 1 is the curl of our fingers, right? So it's going this direction, curl of our fingers. And E, the incident E field number 1, is the uncurl of our E field. So when we uncurl, this is hard to show in my hand, it goes down, as I demonstrated here. And so with that information, the H field is into the page, and we know that omega is 10 to the 11. We can find the direction, or the direction of the wave vector. And so using simple geometry, we can say that this, using this as a triangle, we can say that this, from this angle, is the opposite, and this is the adjacent, right? This is hypotenuse, opposite, adjacent. And so using geometry, we can say that this here is cosine of 60, this here is sine of 60, right? So going in the Z direction is cosine of 60, going upwards in the Y direction is sine of 60. So Z hat, which is the direction, cosine of 60 plus Y hat, sine of 60. And then simplifying this, we get 0.5 in the Z hat direction plus 0.866 in the Y direction. And so using this, we need to find the magnitude of the wave vector, or we need to find the wave number, or the wave magnitude. And so by doing this, we can use the index of refraction. Again, I stated before that doing a good conductor, you cannot use the index of refraction. But since we're in air, right, we're outside of the medium, we can use the index of refraction to solve for the wave number. So velocity is known as omega over the wave number, and velocity is known as the speed of light over the index of refraction. And so combining these two equations, we can find that the wave number, or k initial, is equal to omega over velocity, which plugging this equation is equal to omega times n over c. As we know that c is a constant known as the speed of light, which is 3 times 10 to the power 8. And omega, as we known by the previous page, is 10 to the power 11. And then index of refraction is given to us in the beginning, which is just 1. And so simplifying this, we get 1/3 times 10 to the power 3, or known as the wave number of 333.33. Once we find the wave number, we can convert the wave number and the wave vector to find the direction and magnitude together. Combining the magnitude and the direction, we get 166.66 in the z-hat direction plus 288.667. Once we find this, we already found the initial k, or the wave vector. Now we need to find the direction of the E field. But first, we need to find the actual magnitude. So, again, as previously before, we solved for eta 2, but remember, eta 2 represents the number 2 in this medium. So initially we're solving for eta 1 now. And so eta 1, right, is the wave impedance, which is basically the ratio of the E field and the H field. And eta is also known as eta naught over n. Eta naught is a constant of 377, and n is based on the index of refraction of which medium you are in. Since we're currently outside, we're in air, n is just 1. And since eta naught is 377, our eta becomes 377. And so when we rearrange this equation, we get the E field, the magnitude of the E field is equal to eta times the magnitude of the H field. And plugging our numbers in, we already know, given by the problem itself, we know that the magnitude of the H field is 5 milliamps over meters. We can convert that into normal amps by multiplying it by 10 times 10 to the negative 3, which is just 0.005. Basically, just moving the decimal place from this number over to the left 3 times, which is just 0.005, which would give us a magnitude for the E field 1.885 volts over meter. And so, once we solve for this, we can find the direction and then multiply it. So the direction, similar format as how we solved for the wave vector. We know that this is going down, and since this is 60, this angle right here, this angle is just the right hand angle, which is 90 minus 60, which this angle is 30. And since this angle is 30, we know that this spot right here is also a right angle. So right angle minus 30 is equal to 60. So this angle is also 60. And since this angle is going down, right, we solve this as a right triangle. So making this adjacent and this opposite. And since this is going in the z direction and this is sine, we have the z hat, sine of 60, And since this is going down in the y direction, and this is cosine, we have minus y hat cosine of 60. Simplifying this, we get 0.5 minus 0.866. Once we found the direction and we found the magnitude, we can multiply that and simplify by combining the direction and the magnitude, and we get a vector known as z hat times 1.63 minus y hat 0.94. Now, after doing all of this, we can finally put it into one full equation. So the initial E field 1 is known as, from the direction and magnitude combined, z hat 1.63 minus y hat 0.94, the vector, cosine, because remember, we are dealing with left-hand circle polarization. As stated before, we're dealing with left hand, and it states that the magnitude, or the h field, is 0, 0. This term means that cosine at t equals 0. And so therefore, since we're dealing with left-hand circle and left-hand circle polarization, we must have two terms. That's why it is written as the E field, the initial E field number 1. So cosine, our omega, which is 10 to the power 11 t, minus our vector, our wave vector, which is just 166.66 z plus 288.67z. And so positive becomes negative, so negative 166.66 z minus 288.6 y. And so this is the entire equation, and our units as well, voltage over meters. And so since we found the first term, we need to find the second term, which is sine. And so doing this, we need to redraw the actual graph itself. And so, as shown here, we're dealing with left-hand circle polarization, which again, instead of doing right hand, we're doing our left hand, which K is going up. Our fingers are initial E field number 1, and when we curl, it's pointing out of the page. And the curl of our fingers is the initial E field number 2. So as stated here, positive x hat is into the page, so therefore going out of the page, the direction of the incident E field number 2 is negative x hat. And so knowing this, it just changing the direction and changing the magnitude and changing the term is just what we need to do. So the incident E field number 2 is just negative x hat times the magnitude, 1.885, sine, because we already did cosine, and the second term is sine, times 10 to the power 11 t. And then again, our wave vector becomes, since this is positive, it becomes negative. And then our units. And then we finally combine them into one equation. So the incident E field is equal to the incident E field 1 plus incident E field 2. And that's how we solve for the incident E field. And so once we solve for the incident E field, we can determine the transmitted angle going into the medium. And so since we're dealing with good conductor, we cannot use the typical Snell's law. We cannot use N1 sine incident angle is equal to N2 sine transmitted angle. And we're looking for the transmitted angle. So we cannot use this because we're dealing with the index of refraction. So therefore, we need to modify the Snell's law as K1 is sine of incident angle is equal to beta sine of the transmitted angle. Since we already know what K1 is, as we solved it right here from our incident E field, and we already know what beta is, as beta is right here, the only term that we are missing is the transmitted angle. And we need this term in order to determine the reflection and transmission coefficient. And so, simplifying this, we get sine to the power of -1, or inverse of sine. The magnitude of the wave number, or the wave vector, times sine theta incident all over beta. And so we plug in all our numbers and we get a transmitted angle of 1.11 degrees. And so now, using this information and using the eta 2, we can determine the reflection and the transmission coefficients. So the reflection perpendicular coefficient is known as eta 2 cosine of theta and incident theta minus eta 1 cosine of the transmission theta. And so we're using this equation, again, all over the same terms, just plus. We're using this equation to find the reflection perpendicular coefficient. We know that eta 1, based on solving for the incident E field, is just 377. So eta 2, as we saw in the beginning, for our following parameters, is 5.96 with a phase shift of 45 degrees. So plugging this into our equation, 5.96 phase shift of 45 degrees, cosine of 60 minus 377 cosine of 1.11 degrees, and I just did equal signs to represent that it's the same in the bottom, just positive, just addition. And then we get a reflection perpendicular coefficient of negative 0.989 with a phase shift of negative 0.63 degrees. And then for solving the reflection parallel coefficient, we use this equation. It is almost similar to the same equation, it's just that our transmission theta and incident theta is flipped. And so using the same values before, just flipped angles, we get a reflection parallel coefficient of negative 0.956 with a phase shift of negative 2.6 degrees. And so while we're at here, we can find the rest of the parameters we need to solve for the reflection E field and for the transmitted H field. And so the transmitted coefficients, the transmitted perpendicular coefficient is 1 plus the reflection parallel coefficient, which we solve right here. We add them together and we get a number of 0.0154 with a phase shift of 45 degrees. And then solving for the transmission parallel coefficient, we use a different equation, which is just 2 times eta 2 cosine of the incident theta, eta 2 cosine of the transmission theta, plus eta 1 cosine of the incident theta. So using this, we plug in all our numbers that we gain from the following parameters, and we get a reflection parallel coefficient of 0.0309 with a phase shift of 44 degrees. So having these 4 parameters, we can solve for the reflective E field. And so the reflected E field is when the incident E field reflects off the medium. So the incident angle stays the same, or the reflective angle stays the same. But now the direction of our wave vector is going in this quadrant. And since we know that all of the E fields going out of the page will be the same for each medium. And so since the incident E2 is going out of the page, we can assume that the reflection E field 2 is going out of the page too. But what about the reflective E field number 1? And so to describe how the incident E field is reflected, I can show it as using this following diagram. So this diagram is basically this, but just flipped on its side. And so we know that this is the initial wave vector. This is the reflected wave vector. We know that this is the incident E field 1, right? We can break this vector into its own components. Since we know that it's going down like this, we can break it down that it's going in this direction by this much and this direction by this much. And since this part is tangential to the medium, right, we can assume that is also tangential to the medium in the reflected. And since this part of the E field, incident E field, is going down into the medium, or perpendicular into the medium, then therefore it becomes flipped and it goes up. And so with this knowledge, we can show that the reflective E field 1 goes up like this. And so as you may tell, this is left-hand circular polarization, right? K E1 curl E2. But this is no longer left-hand circular polarization. This becomes right-hand. K ER1 and ER2 goes out. So this becomes right-hand rule. And so with this information, we can solve the direction and find the wave vector direction as well. And so using this information, the reflective wave vector is just shown as negative z hat cosine of 60 plus y hat sine of 60. Again, this is going in this direction, which is negative z, and this is going up, which is positive y. And again, this degree is the same as this degree, as known as this is parallel with this. Therefore, this angle is the same as this angle, and this angle is the same as this angle. And then again, we simplify, which is negative z hat 0.5 plus y hat 0.866. And then we combine that with the wave number, because again, we're dealing in this spot. We're not dealing with this medium yet. We're dealing with this medium, which is just n is equal to 1. And since this is the same wave number, but different wave direction, we can convert it into this wave vector of negative 166.66 z plus 288.66 y. Now, after solving for this, we can solve for the magnitude of the reflective E field. And so the magnitude of the reflective E field is just like this. Oops, sorry. Is just the ratio of the reflective E field and over the incident E field. Again, this coefficient is unitless. It's just a ratio between the reflective E field over the incident E field. And so using this equation, we can move terms around, which we can solve for the magnitude of the reflective E field 1, which again, our coefficient, our reflective parallel coefficient is negative 0.956 with a phase shift of negative 2.6 right here, multiplied by the magnitude of the incident E field number 1, which again, the incident E field number 1 is just 1.885, which we solved for incident E field. We multiply that, and we get a negative 1.80 with a phase shift of negative 2.6 degrees. And again, the direction is the same, is a different direction, sorry, going down. And since we know that this angle is 60, this angle is 30, therefore this angle is 60. And knowing this, we know that it's going down in the negative y hat direction and negative z hat direction. So therefore we solve it. Sine 60, cosine 60, simplify it. And then having the direction and the magnitude, we can combine those two. And then we get a vector of z hat 1.56 and y hat 0.9. And then what we deal with the negative 2.6 phase shift is that we convert it into radians. And in order to do that, we have to go back to our geometry ways, where we multiply the degree by a pi and then divided by 180, which gives us a radiance of 0.045. I forgot to write radians. And so using this, we can solve for the reflective E field number 1, which is just the magnitude times the direction, the vector, times cosine, because again, we're dealing with two terms, times 10 to the power 11 times t. And since our wave vector is negative positive, it becomes positive negative. And then we add our phase shift at the very end, minus 0.045 volts, voltage over meters. And so to find our second term, we redraw the graph. We know that KR is going, the reflective wave vector is going this way. The reflective E field, number 1, is going this way. And so with right hand, our fingers E field number, reflective E field number 1. Our thumb is K. Our curls goes out of the page. And since positive X direction is into the page, then therefore the direction of the reflective E field 2 is out of the page, which is negative. And so again, how we solve for this, we're doing the ratio of the reflective E field 2 over the incident E field 2, which we use the reflective perpendicular coefficient because this is going perpendicular out of the page, perpendicular to the page, right? Compared to this one, which is parallel to the page. And so we rearrange the terms. We use, again, what we solved for, negative 0.989 with phase shift of negative 0.63. And so we multiply the coefficient with the magnitude, we get negative 1.864 with a phase shift of negative 0.63 degrees. And then again, we convert this phase shift into radians to combine it with our equation at the end, which is just multiplied by pi divided by 180, which is equal to 0.01. And then lastly, we combine all these terms together, which the reflective E field 2 is negative x hat times the magnitude, which is negative 1.864, times sine, which is the second term of the right-hand circular polarization, times 10 to the power 11t. And then again, our wave vector becomes, since it's negative positive, it becomes positive negative. And lastly, our phase shift is negative 0.01 voltage over meter. And then to just simplify again, we combine the negative terms together, and therefore this entire equation becomes positive. And then again, I didn't write this down, but the reflective E field is just the reflective E field 1 plus the reflective E field 2. And that's to solve for the reflective E field. And so lastly, to solve for the transmitted H field, since now we're dealing inside the medium, we're using the transmitted angle or the transmitted theta, and now we have a different wave number and a different wave direction, and we're dealing with now with H field. So everything that we do, we need to find the E field, the transmitted E field, and then convert it into the H field. So right here, again, perpendicular, as we said with all the previous examples, the E field perpendicular to the page, we can assume that it's always perpendicular to the page. And so since we're dealing inside the medium, the transmitted E field 2 is perpendicular to the page. And since we're not reflected no more, we didn't reflect, we're transmitted into the medium, we still stay left hand, circular polarization. So using left hand, we can find for transmitted E field number 1, curl is transmitted E field 2, K, the K vector is going this direction. And so when we uncurl our fingers, E transmitted will going down, as shown here. And so to convert this into the H field, we first use the right hand rule to find the transmitted H field number 1. So using the right hand rule, this is going to be a little bit difficult to show, but the wave vector is going over here in this direction, diagonal. Transmitted E field number 1 is going down, and so when we curl, our fingers are going into the page, And since we said that positive X is into the page, therefore it's in the positive X direction. And then since we already solved for one H field, H transmitted H field 1, we can find the direction of the second term. So the second term, since we're still in left-hand circular polarization, we can use our left hand to solve for the H field transmitted to. And so using our left hand, K is going in this diagonal direction. HT1 is into the page. Our fingers are into the page. And then therefore, when we curl, HT2 is going in this diagonal direction, And so, since we know that this angle is 1.1, right? This transmitted angle is 1.1. parallel with this, parallel with that, this angle is the same as this angle. And so this angle, therefore this angle is the same as this angle too. And so since this angle is the same as this one, remember this whole this just becomes a right angle. And so therefore this right angle, we just subtract 90 or 1.1 or 90 minus 1.1, and then we can solve for this angle. And since this angle is also now a right angle, but yeah, this part right here is not a right angle, we can solve that this, whatever this angle is, 90 minus 1.1, which is just 98.89. Don't check my work on that. This just becomes 1.1. Whatever this angle is, 90 minus whatever this angle is, becomes 1.1. And so we can solve for the magnitude of the E field transmitted. And so by doing that, we do the same method that we did, where the transmission coefficient parallel is just the ratio of the transmitted E field number 1 over the incident E field number 1. We move the terms around, and we use the coefficient that we gain, parallel transmission, which is 0.0309, phase shift of 44 degrees. We use that times the magnitude that we solved initially from part A. We get a magnitude of 0.0582 with a phase shift of 44 degrees. But this is just the magnitude of the transmitted E field 1. We need to find the transmitted H field 1. And so by doing that, we can solve it by using this equation, where the ratio is equal to eta 2. And moving terms around, we can solve that the magnitude transmitted H1 is equal to the E field transmitted E field number 1 over eta 2. And since we know that eta 2 is just 5.96 with a phase shift 45 degrees, we plug in all the numbers, and we get a magnitude of 0.00976 with a phase shift of -1 degrees, which is just amps over meters. And then to simplify this number, we can convert this amps into milliamps, which just becomes 9.76 with a phase shift of -1 degrees, milliamps over meters. And we can convert that -1 into a phase shift of 0.017. Again, multiply the 1 with pi and divide by 180, which gives us 0.017. And so once doing this, we can also solve for the transmitted E field 2. Again, doing the ratio of the transmitted coefficient using the value that we got from solving the parameters, 0.0154 with a phase shift of 45 degrees, multiplied by the magnitude of the initial E field, we get a magnitude for the transmitted E field 2, 0.0290 with a phase shift of 45 degrees. And so we can use this magnitude to solve for the magnitude of the transmitted H field 2. Again, the transmitted E field 2 is over eta 2, and it gives us a value of 0.004870 amps over meter. We convert amps over meter to get 4.87 milliamps over meters. Now, using these two values, we can solve for the direction of the transmitted wave vector, which, using the right hand triangle, we can say that since this is cosine in the z direction, and this is sine in the y direction, we can solve it as z hat cosine 1.11 degrees plus y hat sine 1.1 degrees, which is equal to z hat 0.99 plus y hat 0.019. And since we're dealing in this medium, we can multiply this by beta in order to find the wave vector. So again, beta was solved in the beginning as 149,000. We multiply and distribute into the vector, into the direction, and we get 149,000 z plus 291 y. And then we can finally use that to find the transmitted H field 1. And so since we said that transmitted H field 1 is going into the page and positive direction is going into the page, then therefore it's positive x hat multiplied by the magnitude, which is 9.76, cosine, because this is the first term, times 10 to the power 11 times t. And then remember, positive, which becomes negative, negative. We add our phase shift, which is 0.017. And then important to note that since we're dealing with a good conductor, we're inside the medium, we have to account for attenuation. And so in this case, the attenuation describes how fast a signal will attenuate inside the medium. And so the attenuation is the same as the direction of the wave vector. So it's e to the power of negative 149,000 times z minus 291 times y. And then remember to write units. And in this case, we convert it to milliamps, so we need to make sure we stay in milliamps. And so then lastly, we need to solve for the direction of the transmitted H field 2, which is going this direction. We know that this angle is 1.11 degrees. We know that from here to here in the z direction is sine, right? Right triangle. From here to here is cosine. So therefore in the negative y direction, so therefore is z hat sine 1.1 minus y hat cosine 1.1. We simplify it. Z has 0.019 minus y has 0.99. We multiply the magnitude and the vector and the direction in order to find the vector of the transmitted H field 2, which is just 0.1 z hat minus 4.87 y hat. And then we can finally put all of that into one equation, which is just the vector of the transmitted H field 2, and then multiply it by sine, because this is the second term, times 10 to the power 11 plus, and then our wave vector, which is positive, so it becomes negative, negative. We're not dealing with any phase shift because our phases were 45 degrees, so those cancel out. And then we need to make sure we have attenuation, which again is the same as the first term, again in units of milliamps over meters. And then lastly, the transmitted H field is just transmitted H field 1 plus transmitted H field 2, and that's for the transmitted H field.